Good afternoon, this is Statistical Mechanics 504, and it's Wednesday, April the 15th. So we're going to talk about charge systems today. So let me briefly recap what we talked about last time. So what we were discussing was the idea of looking at a system which was charged, composed of two ions. We estimated the regime in which there may be small corrections to the ideal gas behavior due to the Coulomb interactions, and we identified what that regime was. Then what we did was we made a mean field approximation. So we worked out the exact electrostatic energy. We made a mean field approximation that all the ions of species alpha experience the same potential, and so that gave us an average value for the Coulomb energy, or if you like, the correlation energy. So then we embarked on the question of what was the spatial distribution of ions around one particular ion. And the reason that we were doing this was because we convinced ourselves that this correction due to the Coulomb interactions would be concomitant with there being new correlations induced in the system as a result of the charge. And so what we did was we considered one of the charges to be a test charge, and then we asked what is the non-uniform charge distribution around that test charge. And of course, what we realized was that if I have a positive charge in the system, the negative charges will flock towards it, will be attracted to it. But as you go further and further away, the negative ions that are far away will see the effect of both the positive charges and the negative charges, and so they will tend to see a reduced attraction from the positive charge. And so what we set out to do was to calculate exactly that effect. So the way we did it was we said, well, all right, let's have a spatially dependent density of ions of species alpha, a distance r from the test charge. Then, of course, we know that if there's a potential, we know that the distribution of particles in that potential, the density is just going to follow a Boltzmann distribution. So we wrote down equation 1 that you see on the left over there. And then what we said was, how is that potential determined? And of course, that's answered by electrostatics. And the answer is, if I know the charge distribution, then I know what the potential is, and that's given by Poisson's equation. So we wrote down Poisson's equation. So this was Poisson's equation, equation number 2 over here. And that gave us, of course, two coupled equations, which are nonlinear because of the exponential that is in the Boltzmann factor. So then what we set out to do was to expand the exponential and look in the regime where the attraction, the Coulomb potential is weak in some sense, which we'll determine in a few minutes. And so with that, we expanded the right-hand side, and charge neutrality meant that the first term cancelled, and then we ended up with a particular equation for the potential, which I've written down over here. And this equation is essentially the Helmholtz equation. So the length scale that comes into the Helmholtz equation, this lambda, which has units of length, that lambda we can just read off is related to the charges as I've shown over here. So then we ask ourselves, well, if we have to solve this equation, we need to have some boundary conditions. And the boundary conditions are very simple because very close to the charge, the potential has to be Coulomb. The further away you are from the test charge, the more negative ions there are that intervene. And so very close to it, the potential should be a pure Coulomb potential. And so what we're going to do today is we're going to solve this equation and then look at what is the physical significance of the solutions. So let me just tell you how you solve the equation. So we're talking about solving the Helmholtz equation over here. So what I want to remind you is that the Laplacian in spherical polar coordinates has the form shown over here. So in general, if d is the spatial dimension, we can write the radial part of the Laplacian operator as this, and we can also write it in this form over here. So this should remind you of what you did in quantum mechanics when you solved the Schrödinger equation in a spherical square potential. And so the trick is simply to make the substitution that phi is some new variable psi over r, excuse me. And if you substitute that in, what you find is that psi satisfies the one-dimensional equation, which looks like a harmonic oscillator equation with the spring constant being having a negative sign, and so you have solutions being hyperbolic functions or exponentials rather than the usual sines and cosines that you would get for the harmonic oscillator. So in this way, and imposing the boundary condition that as we get to the origin, we see the Coulomb potential, what we end up with then is that the solution is simply phi of r is equal to E z over r e to the minus r over lambda. And you can see that as I make the limit r going to 0, this thing looks exactly like the Coulomb potential, because in that limit, the exponential term just goes to 1. Okay, so that's the solution of the equation, and we can interpret this in the following way. What we say is that the Coulomb potential has been screened what we say is that the Coulomb potential has been screened by the other charges. And now falls off rapidly with distance. So what's happened is, well, our original Coulomb potential was that is now falling off as this, and this E here is actually the charge, not the number 2.7. So what we can interpret this as is the following way. We can interpret this as a spatially dependent charge. So let me write it like this. Let me write it as Q Z over R, where Q is equal to the charge on the electron times Z, or actually I don't want this Z over here, times the exponential of minus R over lambda. And so we can see that Q is now an R-dependent quantity. And the charge increases the closer you get to the origin. So this is the idea then of a sort of a normalized charge. And it's exactly this same idea that happens in quantum electrodynamics. So in quantum electrodynamics, what happens is you have an electron, but what the electron does is it polarizes the vacuum. And so what happens is that you preferentially get positrons excited from the vacuum will cluster around the ordinary electron. And so the charge that you actually see on the electron is the result of the bare electron charge, what the electron really has in some sense, plus the vacuum fluctuations around the charge which screen it. And so the charge of the electron that we observe is what's happening once you get far enough away from the original electron. So this renormalized, we call this a renormalized charge, and then we note that in quantum field theory, you have the same idea, namely that the original electron is surrounded by a screening cloud of virtual particles. And what that does is that reduces the charge on the electron that you see macroscopically. So this idea was really first developed by Stuckelberg and Peterman and Gell-Mann and Lowe. And the latter paper is the one that is the more famous one. It's called Electrodynamics at Short Distances. Actually, I don't remember the exact title. I think that's what it's called. It may be something more fancy than that. And this paper was really the start of renormalization group theory. So not just Gell-Mann and Lowe, but also Stuckelberg and Peterman, who did the same thing. And this renormalization group theory paper, it's interesting because this was written at the time that this was written. This was 1951 to 52, 53. I've forgotten, 50 something. Wait, no, 2. I'll put. And where was it written? Well, it was written in Urbana-Champaign. So this was written at UIUC. And where Gell-Mann and Lowe were working in the summer at what was then the Loomis Laboratory, but it wasn't the Loomis Laboratory, it was the Department of Physics, and it was further down the street from where the present building is. Okay, so that's the formal mathematical solution of this. Now let's try to discuss what it means. So let me draw a cartoon picture. So let's go back to our picture of the test charge. So there's our test charge, and now it's surrounded by this sea of negative charges. So let's draw them like this. So those are the negatives. And that's a positive. So what we've actually what we claim to have found, is that this potential varies as a function of distance away from here, and so what we found is the mean potential phi of r experience a distance r from the test charge. Now, in order for this to make sense, we have an obvious condition that needs to be satisfied. So why would we ask the question? Well, the point is that the phi, so the phi of r goes like Ez over r times x minus r over lambda. And so this quantity lambda tells you the decay length of the potential. So if I were to draw some scale on this curve over here, on this picture, I think that it would look something like this. We'll choose a good color. So basically, this is decaying over a scale lambda. So what we need then is a notion of self-consistency. Now, why do we need a notion of self-consistency? Well, the point is this: we need there to be many negative particles within the distance lambda. And why do we need that? Well, because if there weren't any, if this was not true, then the potential wouldn't be screened, because you need lots of negative particles between you and the positive in order to screen things. So the potential would not be screened. And we're not just looking at, what happens on one particular realization or one particular moment in time. We're looking at the mean potential here. So we need this to be true for our mean field theory. And so it's important that this is a self-consistent approximation for the mean field theory. So what we need then is that we need that lambda should be much greater than the mean distance between the particles. So now you have to work out what is the mean distance. So we know what lambda is. So lambda is given by this formula over here. Where is it? Dum, dum, dum. Here we are. So here is lambda. Okay. So we can write down that 1 over lambda is lambda squared, excuse me, is 4 pi e squared over kBt. And then we need sum over alpha n naught alpha z alpha squared in general. So that's our formula for lambda squared. And the mean distance between particles is going to be the n naught alpha to the minus 1/3. It's just the separation between these ions. So then if you plug that into this formula, then what you end up with is the formula that we actually already saw, namely over here, namely this formula. So this gives you that indeed n is much less than kBt over ze squared cubed. And so in other words, our assumption about when this theory applies is self-consistent. So you might say, well, how could it be otherwise? Well, it could have been otherwise. So it could be the opposite condition. It's not true in this particular case, but in principle it could have been. And if we had found that, that would have meant that the theory is not self-consistent. So you may say, well, surely all of these sort of theories are self-consistent, but that's not true. So an example of a non-self-consistent mean field theory is what happens in phase transitions. So we'll talk about the mean field theory of phase transitions, but let me, whoops, where are we? So what happens in phase transitions? So what happens there? So in phase transition theory, you can do the self-consistence check. I'm not going to show you how to do that. You'd have to take my class on the normalization group to see how that comes about. So you can do this self-consistency check, and what you find is that it is self-consistent, but only for d spatial dimension greater than 4. So above 4 dimensions, the mean field theory, self-consistent field theory of phase transitions works, and for d less than 4, it is not self-consistent. And this is what leads to the interesting phenomena in the critical exponents, what are called non-classical critical exponents. In d equals 3, for example. So all of that's not something that I want to go into, but I just want to show you that theories can predict their own demise, and it's very useful when they do. So the self-consistency check is not something that's automatically guaranteed to come out right. Okay, so now what I want to do is I want to discuss the thermodynamics. So the way I'm going to do that is I'm going to work out, so what is our goal? So our goal is then to calculate the expected value of the Coulomb energy, and then from that, work out the Helmholtz free energy and the partition function and the pressure and so on and so forth. So that's our goal. So let me start off with my claim. So my claim is that from knowing phi, from knowing this, I can then work out phi sub alpha. And what is phi sub alpha? Well, if you remember what phi sub alpha was, this was the potential experienced by the ions of species alpha. And it's not just the potential, it's the mean potential, okay, because we're doing mean field theory. So let me show you how we verify this claim. So what we know then is that we start with phi of r is equal to Ez over r x of minus r over lambda. Okay, so that's our starting point. So then what do we mean by the Coulomb energy, the average Coulomb energy? So that we defined, worked out to be this. It was 1/2 times the volume times the sum over alpha E Z alpha, that's the charge, times the number of them per unit volume, so that's N naught alpha, times the potential by alpha, which is what we want to find. So the way I'm going to compute phi of alpha is we're going to ask the following question, and the question that I want to ask is, what is the potential experienced by the test charge? And that's the question. So let's figure out how to answer it. Well, the test charge is the charge that you have at r equals 0. It's at the origin in these coordinates. So let's have a look at what happens as we take the limit r goes to 0. So as r goes to 0, what does phi of r look like? So let's write it down. So it's Ez over r. That's the first term. The second term is Ez over lambda. Because it's Ez over r times, now we're just expanding the exponential. And then the next term after that is going to be a term that goes of order r, and so on and so forth. So all I've done, so as r goes to 0, I'm just expanding x of minus r over lambda is equal to 1 minus r over lambda plus 1/2 r squared over lambda squared, dot, dot, dot. Okay, so that's all I'm doing. So let's have a look at what those two terms mean. So this is the test charge Coulomb potential. So this, and that comes from the test charge itself. So this part over here, this then must be the potential, or let's say the contribution to the potential, which is due not to the test charge, but to all the other particles in the system. And so, and then this third term, this term over here, order r, this is equal to 0 at the test charge. Yeah, that's not very good writing, is it? Let's take this away, start again. Okay, that's better. Okay, so what then I've shown you is the following. Thus, a test charge of charge Z experiences a potential minus Ez over lambda, so let's call it Z times E, due to all the other charges in the system. So that means that if now the test charge had charge Z alpha, Z alpha E, it would experience a potential of minus E Z alpha over lambda. And so that's therefore the justification for my claim that we can compute phi alpha. And so what I've just shown you then is that phi alpha is equal to minus E Z alpha over lambda. Okay, I went through that argument in some detail because I found that people find it very confusing when they first encounter it. Okay, so now that we've figured out what phi alpha is, then we can compute the expectation value of the Coulomb interaction. So the expectation value of the Coulomb energy is then going to be minus 1/2 V E squared over lambda, the sum over alpha of n naught alpha squared, n naught alpha times z alpha squared. And if you just plug in the numbers, that is equal to minus the volume times E cubed pi over kBt to the 1/2 power times the sum over alpha n alpha z alpha squared, and this whole thing raised to the 3/2 power. And what I mean by n alpha, that's just n naught alpha times the volume of the system. Well, if I know the Coulomb energy, then I can compute the Helmholtz free energy. So I'm going to use a trick to compute the Helmholtz free energy. So what is the trick? Well, the trick is this. I know what the free energy is for an ideal gas. So instead of computing just the free energy, I'm going to compute the free energy difference due to the Coulomb interactions. So the trick is to compute the difference. So how do we do that? Well, remember the formula that we learnt in elementary statistical mechanics earlier on this semester. We learnt that E is minus T squared d by dt of the Helmholtz free energy over T. And we derive that in multiple ways. I'm not going to go over that. And so what that says is that if I integrate this equation, this says that F is equal to minus T times the integral dt of expectation value of E over T squared. So if I were to put in some limits to this from, say, T1 to T2, then this would be actually delta F, which would be F of T2 minus F of T1. So we could calculate that. And so what then we end up with is the result that I'm going to choose the T2 to be infinity. So actually, let me choose T2 to be infinity. So that means that F of T2 is just going to be the free energy of the ideal gas, because as we go to higher and higher temperatures, the Coulomb interactions become less and less important, and so the system will go to the ideal gas. And so that then tells us that F minus the ideal free energy is equal to minus 2/3 times E cubed pi over kBTV to the 1/2 times the sum over alpha of n alpha z alpha squared, all raised to the power 3 Hertz. And so that's how you get the statistical mechanics of the charge gates. Okay, so that's great. So now let's talk about the application to quantum physics. So now let's look at the quantum charged fluid. So this is actually super important, but we're not going to spend time on it in this course. It's very important for solid state physics. So the basic idea is that the same technique can be used for charged quantum fluids and what that really means is the electron gas. So we've already talked about the idea that we have degenerate electrons in the metal, and we use the idea that the electrons in the metal behave as if they are ideal, and we worked out the Fermi-Dirac distribution and so on for electrons in the metal. But we pointed out that when you do that, of course, you're making a ridiculous assumption. You're neglecting the electron-ion interactions, which may arguably be weak, but the electron-electron interactions are certainly not weak. And so why is it justified that you can think of the electron gas in a metal as behaving as ideal electrons? And so this calculation is the one that tells you how you can do it. So the goal is to explain why electrons in a metal behave as ideal fermions. And you can see where the idea is going to work, because we had this picture of the charge sitting over here with some charge, and then around it being some screening cloud. Well, let's suppose the screening cloud now is pluses rather than minuses. So something like that. So this is a screening cloud. Electron is screened by the background positive charge, which is there to make the system electrically neutral. And as long as the length scales allow the lattice distortions to provide charges in this way, then the electron is screened by background positive charge. And so that means that the electron-electron interactions will go to 0 once R is greater than the Debye screening length, this lambda, the screening length. So that's the basic idea. So that's the basic idea. And now what this account leaves out is that the electron gas is degenerate. And so the question that we want to ask is how is the analysis, how is the screening analysis modified for degenerate quantum systems? So that's the answer, or rather that's the question. And so the way that I'm going to answer it, I'm not going to go through it in detail because I think this is something that you should be doing in your solid state physics class. But what I'm going to do is I'm going to work out for you what is the density regime where the screening actually works. So here our goal is more modest. Our goal is simply to compute when the screening is valid, it works. And when I say when, what I mean is what density regime. And we want to ask that because that was the first thing that we did for the classical system. And for the classical system, what we found was that at low density for a given temperature, that's when the screening would work. So now we're going to ask, well, what happens in the quantum case? So first of all, we're going to start by working out what is the condition for the degenerate gas. Okay, so that's easy to answer because that just simply says that the temperature should be less than the Fermi temperature. And so what that means is that, precisely speaking, kBT should be less than h bar squared over 2m times k squared. So the Fermi wave vector was 3 pi squared n over v to the 1/3. And so therefore it will be this thing raised to the 2/3. So that's the first question. The next question we want to ask is when is the Coulomb interaction much less than the kinetic energy? So that's the condition that we're trying to solve. And of course, what we're really looking at is the average Coulomb energy and the average kinetic energy. So let's try to estimate then what those quantities are. So we're going to estimate the average potential energy. So that we would say as well, that's going to be ZE times E. So ZE, whoops, no, not that. So if I have an ion of charge Z and an electron, then that charge is going to be ZE squared. Let me write it in this way, sorry about this. Let me write it like this, ZE times E. So this thing over here is meant to be the charge of an ion. So that's a charge of an ion with charge plus Ze. And this thing over here is the charge on the electron. Okay, and then what do we have? It's going to be Ze squared. So this thing divided by A, where A is something like the mean separation between an electron and an ion, a positive ion. Okay, so that's what that thing is. So my claim is that this A is equal to the following. I can get this by saying, let me keep that there, but let's take this out. So the way I want to answer this, the way I want to figure this thing out, is I'm going to say the following. I'm going to say that there's n electrons in volume V. Okay, we have Z electrons per ion. If that's it, it's valence straight, and so therefore I have n over Z electrons. No, not electrons, ions. N over Z ions per unit volume. And therefore the mean separation between an electron and an ion is going to be much less, or certainly bounded by the ion-ion separation. And that is going to then be Z over N to the 1/3 in 3 dimensions. And so what that then says is that this quantity A, the mean separation A, is then just equal to some coefficient of order unity times Z over N to the 1/3. Okay, so now I know the mean separation, so now I can work out what the mean kinetic energy is. So this factor of Z, I just want to make sure that everybody completely understands that. So that this factor of Z is it's the valence state of the nucleus. So there are Z electrons per nucleus in these atoms. Okay? So now let's ask what the kinetic energy is. So what we require is that the potential energy, so Z E squared times N over Z to the 1/3, so that's the potential energy. And that should be less than the kinetic energy. And so this kinetic energy is then h bar squared over 2m times n over v to the 2/3 times some pi's and so on, 3 pi squared. Okay, and so when you go and then work that out, what do you get? So plugging those numbers in. So the thing I want you to note, let me write this here. Let me clear this up a little bit. It's hard to read. So here what I wanted to say was 3 pi squared n to the 2/3. So what that means then is I've got a factor of n over here, but I've also got a factor of n over here. And so now what's going to happen is that I get that Z, let me write it this way. What I get then is that n should be greater than E squared m over h bar squared cubed times Z squared. So in other words, before I had a condition that n should be less than something, but now I've got a condition that n is greater than something, and this is strange because this is a high density limit, not a low density limit. And so what that says then is that the electron ion interactions are going to be small at high density. And if you do the similar argument, the electron-electron interactions are going to be small when n is greater than E squared m over h bar squared huge, just simply setting z equals to 1. And so then you have this picture of the system. You have a high density of electrons with small density fluctuations. And that, and so this picture is a picture of an interacting electron gas with high density, small fluctuations, and that's calculated in a can be approximated by what's called a random phase approximation, RPA. And this was worked out by David Bohm and David Pines in the early 1950s. And so basically the bottom line is that the electrons are electron-electron interactions. So electrons are ideal in a metal because of two things. So one is screening, and the other is the things that lead to the Fermi-Dirac distribution. In other words, the Pauli principle. So some of you may have heard of the idea of a quasi-particle. So let me just say roughly what that is. So let's just go back to our picture of our screening. So the comment for the electrolytes, well, we had, well, let me just say it this way perhaps. So in all these situations, and what do I mean by these situations? I mean the electrolytes, which I worked out before. I told you about the idea of an electron plus vacuum fluctuations. And I told you about an electron in a metal. So in all of these pictures, what you have is you start off with an electron, and then you switch on the interactions. And then what you end up with is the picture of the electron. So there it is again, plus the screening cloud around it. So I'll write it like this. Trying to show the decay with distance, and this whole object is called behaves like some composite particle. So the scale here, is some Debye screening length, and so then the idea is that this object behaves like some bad color. Let's go back. So this object behaves like a composite particle, or a composite, or if you like, an effective particle, or an emergent particle, if you like. So this composite effective particle is what's known as a quasi-particle. And so this whole idea of starting off with particles and then having some interactions between them that then cause there to be some kind of renormalization of the particle's properties, either in its charge or its mass or spin and so on. So that is a very important theme, not just in quantum field theory, but in condensed matter physics. Okay, so that's all I want to say about the small deviations from ideal gas behavior from either diagrammatic perturbation theory or systems with long-range forces. So are there any questions on that before we go on to the next topic, which is phase transitions?
Professor, I have a question.
Yeah.
Can I go ahead?
Go ahead. Go ahead. Is that Vaibhav's talking?
Yeah. So if you actually look at the fluid, what sort of picture will you have? Will you be actually able to observe these spherical effective particles going about, or you will have a very homogeneous, almost homogeneous solution if the charges somehow balance each other out?
So remember, what we're looking at is a statistical system.
Yeah.
So if you took a snapshot and then measured correlation functions, you would measure correlation functions that this theory predicts. So I didn't talk about what the correlation functions would look like, but you can calculate those, and that's what you would see. Or if you simply did something like neutron scattering or some neutron spin echo or some other scattering. Those are probably the wrong scales, but you would be able to observe these correlations between the objects, so they wouldn't be random.
Okay.
But the real way that you see these things is we'll talk about this a little bit, perhaps more in my class on phase transitions or on emergent states of matter than in this class. But there's a connection between the correlations and the response functions or the susceptibility of the system. And so the real way you would see these things is through the dielectric constant that emerges as a result of these interactions between the particles.
Okay.
So yeah, so these are observable. These are very much observable. Okay, so there's no other questions. Okay, it doesn't seem to be. So let's move on to the next topic. So the next topic is a sort of introduction to phase transitions. And so let's just remind ourselves where we were. So in the previous sections, what we looked at up to now, we looked at the quantitative modifications of the equation of state due to interactions. Excuse me, I'm going to sneeze probably in just a minute. It'll come and go. Okay. Okay, so we looked at quantitative modifications of the equation of state due to interactions. Okay, so that's what we did up to now. So what we want to look at now is the qualitative changes that interactions can produce. So these interactions that we looked at up to now were basically weak. So the next thing that we want to do is ask if the interactions are strong, then that can give us qualitatively new features. And that's much more interesting. Okay, we're much more interesting in making a qualitatively new prediction than we are in just computing the sixth decimal place of some equation of state or something. So what we're going to do in this section then is we're going to look at this in two ways. So we're going to look at this in two ways. One is a rather formal way. And this way of thinking about phase transitions is a way that is rooted in the fact that they reflect non-analyticity in the statistical mechanics. So there's a formal way of thinking about phase transitions as non-analyticities, non-analytic behavior, let's say, in the statistical mechanics. And so when I talk about the statistical mechanics, what I mean is the partition function, or maybe the grand partition function, something like that. So that's going to be our formal way of thinking about phase transitions. And I'm going to derive for you some results which were originally due to Li and Yang. Then what we'll talk about is another self-consistent mean field theory. And this is a mean field theory for the Ising model, for an interacting spin system. I'm going to derive it by a ludicrously simple way, but my point is that we can understand all of the qualitative features of real phase transitions just from doing some very elementary mathematics in mean field theory. So this is a mean field theory for an interacting system, and then what we will get from that is the existence of scaling laws, power law divergences, and so on, data collapse. And this is very, very simple and very powerful. It's not quite correct, but the differences aren't very large for most purposes that they really matter. On the other hand, it's impossible to understand why those deviations exist without having a radically new way of thinking about physics, and that's what the renormalization group is, and that's why it was so important. Okay, so let's start off then with the first part, and this first thing that I'm going to be talking about is the thermodynamic limit. So you might say, well, why are we talking again about the thermodynamic limit? Haven't we done that? Well, the answer is yes, but the point that we're going to make here is that the phase transitions are only well defined in the thermodynamic limit. So another way of saying it is phase transitions do not exist except in the thermodynamic limit. Okay, so let's think about how I want to represent the system. So the thing that I want to explain now is that I want to represent a physical system in a way which is a precursor to the way we think about physical systems in the normalization group theory. So we're going to represent a system with its Hamiltonian in the following way. So I'm going to write it in the following form. I'm going to write the Hamiltonian is some quantity which I'll call a coupling constant K1 times some local operator which I'll call Q1 of the degrees of freedom plus K2 Q2 times the degrees of freedom plus ... like this. And what do I mean by this rather abstract way of writing things? Well, what I'm trying to say is this. So the etas are the degrees of freedom. These q's are combinations of those degrees of freedom. So they represent different terms in the Hamiltonian, such as kinetic energy, and terms in the potential energy. And then these quantities K, like this one over here, this one over here, these things tell you about the strength of these different Q's, these different terms, and so these tell you how strongly this part Q2 is with respect to Q1. So these things are generally referred to as coupling constants. So you might think of the Coulomb potential as being, that goes like 1 over R, or 1 over Ri minus Rj. And then the charges that go in there would be the coupling constants. So these things are known as coupling constants, and these objects here are sometimes known as local operators. So just a simple example. And the K1 might be the charge squared or something like that. Okay, so that would be how we think of the system. So now when we compute the partition function, what do we do? Well, what we do is we average over the etas. So when we write down the partition function, so here's the partition function of n particles, that's just the trace, and we now take our trace over the degrees of freedom, eta of I, e to the minus beta times the Hamiltonian. And the Hamiltonian depends on all of these things here. It depends on the coupling constant, and it depends on the local operators. So once we've done the integral over all the degrees of freedom eta, what do we have left? We have a partition function, which is a function of several things. It's a function of the volume, it's a function of the temperature, and then it's going to be a function of the coupling constants K1, K2, and so on and so forth. And so the partition function then is a function in a multi-dimensional space whose axes are these quantities over here. Okay, so if that would be the partition function. So similarly, if we went to the grand canonical distribution, what we would have is that chi is some function of the same things, but where it's going to differ is it's going to depend, of course, on the fugacity. So it's going to depend upon lambda, and then the other variables, v, t, k1, k2, and so on and so forth, like that. Okay, so that's the idea. Now, what we're going to look at then is the analyticity of these functions. And when I say analyticity, I mean in the sense of complex variables. So we're going to be basically doing complex analysis now on top of statistical mechanics. So the thing that I want to start off with is a definition of a phase boundary. So the definition is this: a phase boundary is the locus of points of chi or z, depending on where you are, where it is non-analytic in its arguments. So let's draw. You might ask, well, why are we talking about phase boundaries? Why don't we talk about phases? Well, the reason is, and it's something I've said before, is that phases aren't really very well defined. So let's remind ourselves about the phase diagram of most matter. So the phase diagram for most matter is just a diagram in the pressure temperature plane. And then what it looks like is as follows. We have a line going up like this forever, which is is separating up the solid phase. Then we have a triple point, and that triple point has a line going out from it that ends in the critical point. So this is triple. And so those lines are the phase boundaries, and the regions over here. So this is going to be just the liquid phase, and this is going to be the gas phase. So the point about why we talk about phase boundaries and we don't talk about phases is the following. Across here, we'll see that there's a first order phase transition. Across here, there's a first order phase transition. And at this point here, at the critical point, that's going to be where the line of first order transitions turns into a second order or a critical transition, critical point. So what is the point about why do we talk about phase boundaries? Well, let's suppose that we start with the system at this temperature and pressure, and we want to go to this temperature and pressure over here. So there's two ways to do it. One is you can go like this, and the other is to increase the temperature to this place, then increase the pressure, and then decrease the temperature and go back there. So there's two ways to go from point A, let's call this point A, and this point B. So we can go from A to B in two ways. And on the first, we encounter a phase transition. And in the second, we don't. And so that tells you then that there is no unique way to define necessarily a way to see that phases exist. So it's easier to define phase boundaries than phases themselves. So phases aren't really exist. So we think that liquid and gas are just equal to basically fluids. Okay, so next thing I want to do, the last thing I want to do today, is I want to talk about the fact that phase transitions are impossible. So let's see how that can be true, and a more precise way to say it is that they cannot occur in a finite system. So let's explain how that comes about. So I'm going to take as an example a interacting gas, an interacting hard-core gas. So maybe it has some hard-core radius, and then it has some long-range van der Waals attractive potential or something. So let's suppose that we're in a volume V, like so. So then you can ask, well, here's my volume. Now let's stick into this volume my particles. So the particles look like this. I stick them all in. Okay, I'm not going to draw all of them. And you can see that inside my finite box, I can include m of v is the maximum number of particles I can stick inside the box. In the box. Okay, so why is there a maximum number? Well, suppose I try to put n particles in, and n is greater than this m, then what will happen? That means that the energy will be so high that z of n will go to zero. Let me say will tend to zero. I should say really, and it will tend to zero as the hard core radius repulsion goes to infinity. So what that means is that if I write down the grand partition function, that's going to be a function of the fugacity, the volume, and the temperature. So what that's going to be is that's the sum from n is equal to 0 up to this maximum value, m of v, of lambda to the n, and then the partition function of the system with n particles. And this lambda is the fugacity e to the beta mu. Okay, so the the key point, and we'll talk about this next time in more detail, is that this is a polynomial. And it's a polynomial in the fugacity lambda. Most importantly, not just that it's a polynomial, but the coefficients of the terms in the polynomial are Zn's. Okay, so the coefficient of lambda squared is Z2, the coefficient of lambda cubed is Z3, and so on and so forth. And the Z's, Zn's, those are the sums of e to the minus beta energy type terms. And so because I have e to the minus x, these terms here are non-negative. Okay, e to the minus x can never be negative. And so what that means is that the z's are always positive. And so then what I have then is that chi is a polynomial in the fugacity with positive real coefficients. Okay, well, that's where I'm going to end for today, because what I want to do next time we're going to study the analyticity of chi, and we're going to do that by looking in the complex lambda plane. So the fugacity is, of course, a real variable. If I want to understand the analyticity, then what I have to do is I have to generalize and look into the complex plane. And so what we're going to be doing is looking at the system with complex fugacity and then looking at the poles of the grand partition function in the complex fugacity plane. Okay, so all of that's is something to discuss next time. So I'm going to leave it there. So I'm going to turn off the recording and